All right, let's dive in. Today we're doing a complete walkthrough of a system that absolutely changed the game for building massive, always-on services, Amazon's Dynamo. It's a true classic in the world of distributed systems.
We're going to break this down into 4 key parts. First, we'll tackle the big, fundamental question of consistency that every one of these systems has to deal with. Then, we'll peek under the hood at Dynamo's architecture. After that, we'll get into the nitty-gritty of reads, writes, and versions. And finally, we'll see how it's just masterfully built to expect and handle failure.
Okay, Section 1. Before we can really get what makes Dynamo so special, we have to wrap our heads around the core problem it was designed to solve. I mean, think about it. When your data is spread out across tons of different computers, how on earth do you make sure everyone is seeing the right thing at the right time? That, right there, is the central challenge of data consistency. And that brings us to the core philosophy behind Dynamo, eventual consistency. The promise is actually pretty simple. If things quiet down and no new updates are coming in, then eventually everyone who asks for the data will get the same latest version. So instead of making everyone wait around for one perfectly synchronized state, Dynamo says, nope, we're going to prioritize speed and making sure the lights are always on. It's a deliberate trade. Give up a little bit of immediate consistency to get rock-solid availability.
Okay, so that's the big picture. But what if we zoom in a little? That's where client-centric consistency comes in. This idea is a bit more personal. It asks a different question. What if we only need to guarantee consistency from your perspective? For the single person or application making the request. As long as the data you're seeing doesn't do anything weird like go backward in time, maybe that's all the consistency you really need for your session.
This diagram here, it shows that exact scenario perfectly. Just imagine you're on your laptop, maybe you're moving around, and you connect to a completely different server in Amazon's massive network. You're now talking to a totally new copy of the database. Well, client-centric consistency is the promise that this new server isn't going to show you data that's older than what you just saw a few moments ago. It keeps your own personal timeline of what's happening straight.
And this brings us to what is basically the unbreakable law of distributed systems, the CAP theorem. It's a simple but profound idea. It says that when the network breaks and servers can't talk to each other, you have to make a choice. You can have perfect consistency, where everyone agrees on the order of things. Or you can have 100% availability, where the system always answers. You can't have both during a failure. And for Amazon, this was huge. Dynamo looks at this choice and says, yep, we're picking availability every single time.
So, with those big trade-offs in mind, let's actually peel back the layers and look inside Dynamo itself. How is this thing actually put together to deliver on that promise of high availability?
Dynamo fits into this family of databases called key-value stores, and honestly, they're as simple as they are powerful. Just forget about complex tables and all that. Here, you have a key, like a word in a dictionary, and it points to a value, its definition. That's it. It's an incredibly powerful building block for huge services like Amazon S3, and you can see it's inspired a whole lot of other successful systems too.
Okay, this slide is absolutely crucial because everything about Dynamo's design comes from these goals. And I want to call out 2 of them. First, that top one. Failure is the norm. That's not being pessimistic, it's being realistic. The system was built from day one assuming things will constantly break. And second, the explicit choice we just talked about. Availability is more important than consistency. That's the CAP theorem playing out right there in the design goals.
So how do you manage all this data across, maybe thousands of machines? Well, Dynamo uses this incredibly elegant trick called consistent hashing. The best way to think about it is like a clock face. You take a piece of data, turn its key into a number, and you place it somewhere on the ring. You do the same thing for your servers. So to find where a piece of data lives, you just find its position on the ring and walk clockwise until you hit the first server. It's a brilliant way to spread the load.
All right, we know where the data lives on the ring, but how do we actually talk to it? Let's get into the mechanics of reading it, writing it, and crucially, what happens when things get a little out of sync.
At first glance, the API looks almost too simple, right? Just get to retrieve something and put to store it. But the real magic, the secret sauce, is hiding in plain sight in that put command. It's that little context object. That thing is the key to everything because it holds the data's entire version history, which is how Dynamo manages all those messy conflicts we're about to talk about.
So, Dynamo uses this thing called a quorum system to basically decide what done means. Let's look at these common settings. N is simple. It's the number of copies of your data you keep, usually 3. W is your write quorum. How many copies have to say, yep, got it, before a write is considered a success? And R is the read quorum. How many you need to hear from to call a read successful? So with W and R set to 2, you don't need everyone to agree, just a majority.
Okay, let's follow a write request on its journey. It kicks off when a coordinator node gets the put command. That node creates a new version for the data, writes it to its own disk, and then shoots it off to the other replicas. Now here's the key to Dynamo speed, right there in step 5. It doesn't sit around waiting for all of them to reply. As soon as it gets back W1 acknowledgements, it immediately tells the client, "We're good, success." That's what makes it so fast and resilient.
Now the read process. This is where things get really interesting. The coordinator asks the replicas for the data and waits for R of them to answer. But what happens if they come back with different versions of the data? This is the most important part. Dynamo doesn't try to be the hero and pick a winner. It basically just shrugs, bundles up all the conflicting versions, sends them back to the application and says, "Here, you deal with it." The responsibility is on the application to sort out the mess and write back a new, correct version.
And this diagram? It's the perfect way to visualize how Dynamo keeps track of all that history. It uses something called vector clocks. Just think of it like a family tree for your data. You can see the clear lineage from D1 to D2. But then, a conflict happens, and the timeline splits into 2 different branches, D3 and D4. The magic is when a client comes along, reads both of them, figures out the correct state, and writes back a brand new version, D5, that actually merges the history from both branches back together.
All right, for our final section, let's really dig into how this whole built-to-fail philosophy actually works in practice. What are the clever tricks Dynamo uses to stay online when inevitably servers start crashing? This choice for availability really shines in one core principle. The system is always writable. And the best example? Think about an Amazon shopping cart. Amazon would much rather let you add that item to your cart, even if the network's a bit flaky and it creates a temporary disagreement, than to ever tell you, "Sorry, the site's busy, try again later." It prioritizes your action, accepts the write, and worries about sorting out the consistency later.
So that brings up a pretty obvious question, right? If failure's normal and one of the servers that's supposed to be holding a copy of your data just vanishes, how does the system possibly cope without breaking its promises? The answer is this really slick mechanism called hinted handoff, which you can see right here. When a write is supposed to go to a node that's down, a healthy neighbor just steps in and temporarily accepts the write on its behalf. It holds onto that data with a little note, a hint, that basically says, "Hey, this actually belongs to our missing friend over there." Then as soon as the original node comes back online, this temporary guardian hands off all the writes it was holding. It's a fantastic way to make sure no writes ever get lost, even when a server's down.
But there's an even bigger, more persistent problem just keeping all the replicas in sync over the long haul. Tiny differences can creep in. The really naive solution, shown here, would be for 2 servers to just exchange a list of every single piece of data they have and compare them. But on a huge drive with terabytes of data, that's millions of items. It's a non-starter. Way too slow, way too much network traffic.
And this is Dynamo's brilliant solution, a data structure called a Merkle tree. Instead of comparing millions of individual items, you build this tree of hashes. You hash your data at the bottom, then you hash the hashes, and you keep going all the way up until you have a single hash at the very top, the root hash. Now, for 2 servers to check if they're in sync, they only need to compare that one root hash. If it matches, they're good. If it doesn't, they can quickly walk down the tree to find exactly where the difference is. It saves a massive amount of work.
And last but not least, in a giant cluster with servers coming in and out all the time, how does anyone keep track of who's in and who's out? They use a gossip protocol, and yeah, it works pretty much exactly how it sounds. Every second, each server just randomly picks another server, gives it a call, and they trade all the news and rumors they've heard about the cluster. That information spreads like, gossip. And very quickly, the entire cluster gets an accurate, up-to-date map of itself with no central boss telling everyone what to do.
So we'll leave you with this final thought. Dynamo's entire design really flips the script on what success even means. By building a system that assumes from the ground up that things will break, it proved you can build something far more resilient and scalable than a system that just pretends failure won't happen. It's a total shift in how we think about building for the real, messy world.